Now let's look at how we can develop these Strut and tie models, because what we have understood is, yes, we can develop a Strut and tie model and then analyze this structure. But the question is how to develop this Strut and tie model, isn't it? This is the question. So you can see that I have written here about various approaches: elastic stress distribution method, load path method, automated topology optimization method, referred to as the performance-based optimization method, or PBO. Now I've said think practical. Think practical means it is very important to think about which practically you can implement, not just something which is not practically feasible. It is important to obtain a simple, easily constructed arrangement of the reinforcement. This is very important because more and more complexity you introduce in your design, you can also think that while constructing those structures, there will be other problems. And sometimes you will find that instead of the cost saving, it can actually incur more cost when you actually construct them. So let's look at the approaches one by one. The first one is the elastic stress distribution method. The Strut and tie model is constructed by orienting struts and ties to the mean direction of the principal stress trajectories. This is one of the, understood, isn't it? If we have the principal stress trajectories, we can actually orient the struts and ties to the mean direction of them, and then you can construct the Strut and tie model. These trajectories are obtained from the linear elastic finite element analysis on an uncracked concrete member. You see, concrete is uncracked and we are doing linear elastic finite element analysis. Very important. This is very important here. Now, what is the problem? The problem is the model may differ from the load path at the ultimate limit state due to the uncracked assumption, because we have said that we are analyzing for an uncracked scenario, but after then the cracks will appear. So there will be a change in the model. This is sometimes becomes tricky. So that's why we are saying that at the ultimate limit state, the models may differ. So what people do is sometimes people do different models, one for serviceability, one for the strength. Though it happens that it involves a lot of work and sometimes people don't do that, but it's good to know that such things are actually possible. If really, really required, one can go for a model for the serviceability purpose and then another one for the strength purpose. That is the ultimate limit state. So that's your elastic stress distribution method. Continue to the second one, which is the load path method. All the forces acting on the structure or D region are determined to ensure that it is in equilibrium. Suppose we are designing a structure like this, arbitrary one, which is your D region, right? And it is subjected to different kind of forces or reactions, whatever. You have to ensure that this D region is in equilibrium with respect to all these reactions and the forces which is subjected to. If this portion is not in equilibrium, that means there's no point in designing that because it's not in equilibrium. So then how do you design that? Okay, so this is an important thing to think about. Okay. Okay, that all the forces acting on the structure or the D region are determined to ensure that it is in equilibrium. Very, very important. Yep. So that is basically the first step. Then the stress diagram is subdivided so that loads find their way from one side of the structure to another. That is from the point of application of the load to basically the support. Load paths tend to take the shortest path from the applied load to the reactions. It always, nature does that. Plot all load paths in the direction of applied loads. Now, these are the description of how this method is applied. Further struts and ties must be added for transverse equilibrium. You see, very important, transverse equilibrium between the nodes if needed. Now, the best possible model, loads follow the path with the least force and least deformation. Because the ties are more deformable than the struts. Why they are more deformable? Because the ties are subjected to axial force, so they can subject it to more, extension deformable. And so a model with the least member and least number and the shortest ties are the best. So you have minimum number of members and the shortest lengths of ties. They are the best model. So you can see what we are saying here is we can have different possible models, but we are trying to look at what is the best model in this scenario and then analyze that. Okay. Now, minimum length of ties based on the principle of minimum strain energy, SCLAC derived a criterion for the ideal arrangement of strut and ties, and this is given by this. Where Fy is the force in the ith member, strut or tie, Li is the length of the ith member, strain epsilon I is your strain in the ith member. Now, I am not going into the details of this one now at this point of time, but yes, feel free to look at it, and if you're interested, let me know. But this is a general criterion because we are trying to see that what is the best arrangement possible, what is the best load path, because once you can understand that yes, so that's the behavior of the structure, that's the load path, that means we can easily design the structure. Now, the third approach, which is the topology optimization. The strut and tie model can be obtained using the topology optimization. You can optimize the topology and get one. This is a mathematical approach. Usually, numerical methods are employed using the software. Yeah, usually what happens is you have different software. If you look at even the traditional one, like you can use MATLAB, you can use ANSYS, different, and Abacus. So all the software, finite element softwares will have some optimization model, though there are some dedicated ones you will find. So what they do is they usually use the numerical approach to optimize the model. Now the topology is optimized based on certain required performance. That means maximizing the stiffness, for example, for a certain volume of material. Now I'll give a quick example. This is a classical Mitchell arch problem. You can look up these things. Okay, so what we're looking at is if the beam is subjected to this kind of concentrated load, can you optimize the beam so that the beam uses least volume of the material? Okay, still it is able to carry the load. So what we are trying to do is we are trying to find out that what is the minimum weight of the beam in this case, for example. Okay, or we could say yes, we are maximizing the, well, that's okay, don't go into that. Let's think in a very simple way. We are trying to look at that, what is the load path in this case? So what happens is once you know the load path, you will see what part of the structure is important and what is non-important. So in this case, one can easily think of this. So you can see there's a direct load path there. Can you see that? So that's the direct load path. That means if you optimize this problem mathematically, you will actually see that. So this is the triangle. And then what is happening to these materials? That means these materials are not being used to carry the load. That means in such a scenario, your optimized structure only can be thought about this, only this portion, right? Yeah, because the outside material is not used for carrying the load. So they are not contributing. But you can see the practical limitation of that. If you just remove the material from here and here, then the structure will be triangular. Is it that we want? So you can see that there are different limitations of these kind of things, because mathematically we can get any optimal solution. The question is that whether you can use that solution, okay? So this is the optimization problem. So what we do is we have an objective function. For example, we want to minimize something. For example, we want to say maximize the stiffness, or we want to minimize the weight. Then there will be some kind of constraints. Constraints. You have to abide by or follow those constraints, and then go for minimizing or maximizing whatever the objective function is. Okay. So that's the optimization problem, and that's the topology. Means we are trying to optimize what is the topology, which is our optimized topology in this case. Note that all these approaches can lead to similar triangulation or truss type model. This is very important. You can use different approaches and we come up with a very similar solution, and that's what we find in reality. Let's look at example 1. We will use load path method to develop the strut and tie model for the design of this deep beam. You can see this one, how deep the beam is. That's a very deep beam. Now you can see it is subjected to some sort of trapezoidal load. Okay. Now, how are you going to design that? You can see that your traditional design method will fail here, because this is very, very deep. Determine the forces acting on the D region. That's the first step. Now, what happens is, what we can do is we can actually replace this one, because we see the distributed load. What we can do is we can think of, okay, let's consider or think about calculating what is your resultant, isn't it? For example, for this area, this is your resultant. For this area, that is your resultant. So that's the resultant reaction, or you could say the resultant force. And then we are thinking, because once you have this concentrated load in this form, or the resultant, it is easy to calculate the load path. Once you have the like this, we have joined, you can see C and A and D to B, D and B. That means you have directly connected those 2 points, the point of application of the loads to the support, and then we get these load paths. And then at the next step, what we do is we add these 2 lines. Why? Or I will say these are the 2 paths, load paths we add. Why? Because the whole structure has to be in equilibrium. If you look at this joint, or even any this C and D, none of the joints will be in equilibrium if we do not have this horizontal member. And that's why it is very important to note in this case that yes, we need to have these horizontal members so that all the nodal equilibriums are set. All the nodal equilibrium equations are satisfied. That means all the nodes are in equilibrium. Okay, so very important. Do not think that just directly connecting C and A gives me the load path. You have to check that all the nodes are in equilibrium or not. Example 2, this is a bit more involved one, but we'll see that how we can use this method, this load path method, to calculate the or to develop the Strut and tie model. Okay, so it's a 6 meter long beam and 3 meter deep. So again, that's a deep beam. L over D ratio is 2. Can you see that L over D ratio is 2, which is very, very high. Okay. So what we are doing is draw the load path from E to A, because that's the direct one. Yes, that's fine. And then draw the load path from E to C. That's in the dotted line. But what we can see is that the load path is very, very low. So in this case, it is less than 45 degrees. People tend to have not very slant members, because very slant members has a problem. So that's why what our observation shows, that we don't want some members which are very slant. People usually go for 40 to 45 degree. So in this case, it is less than 45 degree. So what we have done is we have drawn a line, which is the angle of 45 degree here at C. So what we are saying is we are designing, or I will say developing, a load path with this 45 degree condition. So that's your 45 degree. And then draw the load path from E to B with 45 degree. That means this line is parallel to that. And then what we do, we actually connect this AC, add tie AC for transverse equilibrium at A and C. A, C, B, every node should be in equilibrium. Okay. And then add tie BD with 45 degree for force equilibrium at node B. So you can see, even in this scenario, node B will not be in equilibrium. A and C will be. So then what we have done, we have drawn a perpendicular, add tie BD with 45 degree for force equilibrium at node B. Okay. So you have another 45 degree line here. That means this will be perpendicular. And then we have joined E and D to complete the load path from E to C. And this is your complete Strut and tie model. So what can you see? Instead of drawing a direct load path from E to C, because it is becoming very slant, we have got an alternative load path, and we will design accordingly. You can see this one. This is very important. Follow the guidelines, because the guidelines, if you have 2 slant member, then it doesn't work. So as a result, we need to have an alternative load path. This is an alternative load path in this case. All the dotted lines are the struts. Yeah. Remember the dotted lines, whatever we are showing, they are the compression members. So they are the struts. And this is the tension member tie. Okay. Yeah. Because this is a solid line. So solid line is represented by or I will say tie is represented by the solid lines and the struts are represented by dotted lines. So you can see this interesting approach and excuse me, following the guidelines, we have come up with a load path, and from that load path, this is your Strut and tie model. So this is your load path, right? And then we have come up with this Strut and tie model. Or basically one could think of the load path is the Strut and tie model. Now we look at some of the examples of Strut and tie model, which is obtained from based on the topology optimization. For example, if you have your deep beam like that, then you have this, your Strut and tie model is like this. Can you see this one? So this is done by the software. Yeah. So that's your load path. Now, if you compare with the previous one, you can see this is the same. And that's what I've said, compare with the previous slide. That means we have used two different approaches. The earlier one, this is the based on the load path method, and this is based on the software. That means performance-based optimization. But you can see both has come up with the similar solution, isn't it? So that's the beauty. Now, Strut and tie models vary with span to depth ratios. For example, you see this one when L over D is 2. This is a very direct load path. As the L over D ratio increases, you can see that there are a number of members. So yes, the load path is there, but there are a number of members that appeared. When L over D equals 4, it actually just looks a very, very nice truss, isn't it? Proper truss. L over D equals 4. Okay, so you can see this is an interesting observation. That means the Strut and tie model is not fixed. If your L over D ratio changes, the Strut and tie model will also change. Some more examples, deep beam with openings. So you can see this one in this case that you have these openings here, and then you have the software results, and this is the Strut and tie model. You can see this, there's a bit of more members here because there's opening there. That's a distribution zone you can think of, yeah? Sorry, not the distribution, it is a disturbance region. So that's why we have this extra members there. Now, concrete in this portion is only subjected to compression only, but the major body here is all subjected to compression. Now, this opening knee joint and the closing knee joint, which we have talked before in this our detailing module, we can see this interesting thing what we can come up with. Okay, let me explain this problem differently. If you look at the opening knee joint here, which is basically a beam column junction, why is it opening knee joint? Because if you look at the direction of the bending moment, as if that it is trying to open the joint. So it is trying to open the joint actually means, so this is, beyond these solid lines represent the tension, that means it is trying to open the joint. And the dotted line is actually in compression, isn't it? Yeah, so the dotted lines is basically the compression member, this is your tension member. So that's Strut and that is tie. So if I write that here, this is your, sorry, UT Strut, and this is your tie. Can you see this interesting problem? If I tell you that design the detailing of this knee joint, it's not very straightforward based on what you have learned before. But what we have done instead, we have developed a load path using the software in this case and have done like this and got this one. So we can now follow this one and develop this Strut and tie model. And now you can see, you can follow this Strut and tie model to detail the joint. That's the beauty of it. So this is a very important application of Strut and tie model, I'll highlight it here, that this is a detailing problem, right? So detailing is becoming challenging. Why is it becoming challenging? Simply because we don't know what is the load path. The load path actually changes, isn't it? The load is actually, it changes the direction. So because we have the problem of this detailing, what we have done is we have developed a Strut and tie model. Now, once the Strut and tie model is developed, it looks like that. Now what we can do, we can follow that model and then detail. That means all these tension members, so you can see we have provided tension zone the reinforcements, compression also we have provided the reinforcements, and because there's a bending here, what happens is that you can have this member slightly, gap, it's probably, you can see there's a gap there. One thing I'll mention, if there's a gap, then you have to provide skin reinforcement. Otherwise, if you can provide very close, then yes, it is acceptable. And then you have these additional members. What are these additional members? These are additional members which is corresponding to these ties. Why you have provided like that? Because if you do not provide them, you'll have the tensile cracks in all those regions because you are pulling like this. So there will be all cracks in this region. You can see this one, right? Because concrete is weak in tension. So the cracks which are developed or which will develop because of this problem of this tensile member, the concrete being tension. In order to take care of the tensile load, we have this diagonal reinforcement provided, which will take care of that. You can see this is an interesting application of the Strut and tie modeling for detailing. I'll say this is a detailing application. Okay, this is a detailing application. Even the next one, which is the closing knee joint, is also a detailing application. Similarly, what we have done is in this case, so you see the moments are like that it is actually closing the joint, not opening like the previous one. So I've said identify the differences with the previous slide. The direction of the moment is such as if it is closing the joint rather than opening. So there's a tension which is outside, along the outer face. So you have the main reinforcement here. So the top reinforcement is actually bend and then going down, or the column reinforcement is going like that. You can think it either way. But because there is a gap in this case, we can actually provide what is called additional or skin reinforcement. Because if there's a too much gap between these two areas, then you have to provide that. Otherwise, you get crack in this region. And you can see the vertical reinforcement is going straight, and the horizontal reinforcement for the beam will extend up to this point. Okay. So it is good to compare with the previous slide, because in the previous slide, you have this reinforcement. The outer column reinforcement was becoming directly as the beam reinforcement. And then the beam bottom layer was just finishing here. Okay. And then we have these stirrups or the rings. Very important, what I want you to do is spend some time in understanding the behavior of these two types of knee joints, opening joint and the closing joint, and see how we are applying this Strut and tie modeling to do an excellent detailing. Okay. Any question?